We're going to take a look and see how to utilize Excel to help us facilitate the computations for the advanced or the improved Euler's method. And so remember our formula for our improved Euler method, and it's a pretty long one. To get to the next y, which we're going to call yn plus 1, that's going to be equal to yn plus h over 2 times f at x and yn, and then plus the function, all right, in this case it's going to be our f, but now it's going to be the next step. So that's going to be xn plus 1, comma, and now the next y is predicted by the usual Euler formula, or the original Euler formula, y sub n plus h times f at xn comma yn. Alright, so imagine trying to type this into one cell, and you'll probably realize that it's going to be almost an impossible task for us to do efficiently. And so the suggestion may be, instead of just trying to program it in all one cell, maybe to break it up into some smaller cells, so divide and conquer. So maybe if we figure out what this fxn yn might be, and then we can go through and try to figure out what the next y might be, so that way we can figure out what this might be. So we can start plugging things in and making it a little bit easier on ourselves, as opposed to trying to go through and compute this all at once. Alright, so we need a number of iterations, and you might recall that the initial, the differential equation was y prime equals 4x minus 2y. And the initial condition was that y at 0 was equal to 2, and we are looking for y at 0.5. Alright? And we're also given that the step size that we're asked to use is 0.1. So let's start out with a number of iterations, n. We have our xn, and then we have our yn. Alright, now the good news is with n, since xn is going to start at 0 and yn is 2, and each of the step sizes is 0.1, and we're looking to get up to 0.5. So we're going to have 0.1, so we just keep adding 0.1 because that's the step size. And then we're going to stop when we get to 0.5. Right? So now this is iteration 0 right here, because that's the first one, and then we can just kind of drag that down. So this is 1, 2, 3, 4, fifth iteration. Now we don't know what the next y is. If we did, then we wouldn't have to do the problem. Alright, but what we should probably do is let's start by finding what the next y is using the original Euler's formula. Alright, so that's going to be our y, or actually we could just find f at x and yn, because that's going to be part of our formula. Alright, so let's go ahead and figure that out. So that's going to be equal to 4 times the current x. So this is going to be f at xn comma yn. And that's going to be equal to 4 times the current x, which is stored in now cell B2, minus 2 times the current y, which is stored in cell C2. All right. Now what we can do is we can figure out what the next, so that's going to be the first part of our formula. Now we can figure out what this is. All right, and this isn't too difficult to figure out because, well, we know what the next x is. All right, so f at xn plus 1, n plus 1 is just going to be in the next cell for x. So this is going to be our f at xn plus 1, comma, y sub n plus h times f at x and yn. Alright, so that's going to be equal to, and I'm going to just drag this over a little bit. So it's going to be equal to the x value 4 times the next x, which is now in B3. And if you want to, you could just click in the cell to make it easy on yourself. So 4 times whatever's in this cell. And then minus 2 times this yn plus h times fxn yn. Alright, so that's going to be 2 times the quantity of yn, which is going to be 2, plus the step size, which is 0.1 times f times 0.1 times fxn yn, and that's actually going to be right here. Right? So notice that all I'm doing is I'm just kind of clicking in the cells as to kind of coordinate with this formula. Right? And then I'm going to close parentheses. It looks like I might have made a small error in there. It looks the same thing to me. So I hit enter. It looks like I have to reformat this. I might have been using it for something else, so I'm going to format it and just make it a number cell to 2 decimal places. That's fine. Well, we can just make it into a general cell. And so we get negative 2.8. Right? And then the last thing we're going to do is we're just going to figure out what the next y is. So in this case, that's going to be equal to, now I'm just using the formula, current y, which is yn, which is 2, plus h, which is 0.1, divided by 2, times the quantity of fxn which is this value right here, plus fxn plus 1 yn plus h times fxn which is this cell right here. We're going to close that out, we're going to hit enter, and we get 1.66. That's the same value that we got when we did this by hand in the previous video. Alright, and when I say by hand, I mean without Excel. Now remember, in the previous video when we did this without Excel, we had to go through and we just had to rewrite everything. Well, the good news is with Excel, we can just go and use and just drag it down because Excel remembers patterns. Now one last thing that we should do, we should say in this cell, the next y is going to be equal to whatever's right here, this f2. So this is going to be equal to f2 right now, because that's our next x. And then what we're going to do is we're just going to drag this down. Now we're just going to get a bunch of zeros. And we're going to drag this. And it's not looking too promising yet, but as we go along, it's going to get a lot better. All right, so we just drag this down. Right? And this is our answer right here. So what we're suggesting is that by the improved Euler method, y at 0.5 is 1.11221953. All right, now the question is, how close are we? Recall that the exact answer was y is equal to 2x minus 1 plus 3 over e to the minus 2x, or I'm sorry, 3 divided by e to the 2x. And that was the exact answer we got in the previous video when we solved this analytically. So let's go through and see how good of a job we did to be able to use, or how good of a job Euler's method, the improved Euler's method does. So let's insert a couple columns here. This is going to be y actual, and then this is going to be our error. All right, so the y actual, now remember, all we're going to do is we're just going to substitute in for x right here into this solution. So y actual is going to be equal to 2 times x, which in this case is b2, minus 1 plus 3 divided by e to the 2 times whatever's in this cell. That's the exact value. And of course the first one should be 2, otherwise it's not a proper model. We're going to drag this. Alright, and we look and these are pretty close to one another. So that's good news. Let's figure out what the error is. Alright, we can say equal absolute value. And remember your formula, it's going to be the approximate, which is yn. So in this case, that's going to be this cell, minus the actual, divided by the actual. Now the first one should have 0 error, obviously, because the model predicts it exactly. And then as we drag along, what you'll notice is that the error is extremely small. Can we get a percentage? Well, we can just right click, we can format the cells, and we can click on a percentage. Let's just approximate to 2 decimal places, and notice that we're below 1% error. So that's really cool that we were able to figure out what this value is to less than 1% error. All right. Now, of course, if we want a better approximation, we can use smaller step sizes. All right. So we would conclude the problem here with what was asked. But let's just see what happens if we start changing the step sizes. How good of an approximation can improved Euler's method do or give us? So let's just use this time. Let's use 0.5. All right. And I'm just going to drag this. Probably need 0.1 here to establish the pattern. And I'm just going to drag this. And remember, what we want to do is we want to get to 0.5. All right. Now, if I drag everything, that's not really going to help us too much, because remember when we hard programmed this, remember we hard coded some of the step sizes. All right. So when you're going back, if you change the step size here, you have to change the step size in all of the different algorithms that we used. All right. So now this doesn't affect us, but I'm just going to drag it down. All right. So over here, I'm going to drag this, and I'm going to change this to 0.05. And then I'm also going to change in here this to 0.05. All right. And then what we're going to do is we're going to drag all the cells that had a change. All right, so I'm going to change this one. So we're going to drag that. Oh, no, I'm not. I'm going to start here and drag that, because the first one was hard-coded as 2. And then we're just going to drag the y-actual down. We're going to drag this one down for the error. Now notice the error is going to be astronomically high at this point. That's just because we haven't dragged the other cells yet. All right, so we're going to drag this one. We're going to drag this guy. And then, so now here's where we're really hoping that the error is going to change. We're going to drag this. And this time what we notice is that we have a much smaller error. Remember last time it was 0.78, which was actually a pretty good representation. Now it's 0.18. That's even better than what we thought. Just to show how powerful this is, now let's change it to, let's say, 0.01. All right, so we change that to 0.01, which means we're going to need 50 iterations. And this is the beauty of Excel, is that in a matter of a moment we can change all of this. So we're going to just have 50 iterations. I'm going to drag this. The next one will be 0.02. And I'm just going to drag all of this. In fact, you could just double click. You can just drag it. Alright, so I'm going to have to drag all this all the way down. And again, we have to change the step sizes. Alright, so I have to change this to 0.01. And then I have to change this to 0.01 as well. All right. And just like we did before, we're going to drag. So we're just going to drag this all the way down. All right, so it might just take a moment to do, but no problem. All right. So it's really exciting for me, because now we're going to see how good of an approximation this gives us. Alright, so obviously we still have 100% error because we haven't changed all the cells yet. Okay, so we're going to drag this down. And we're going to drag this down. Now remember, we changed the H. So that's going to drag this. And finally, we go over here. And this is the one that we're hoping gives us a really good approximation. Alright, so we're going to drag this. Alright, and now check this out. These numbers are really close to one another. In fact, we're within not 1%, not 100th of a percent, or not 1/10 of a percent, but 100th of a percent. And in fact, there's almost no error, or at least it's error to at least the thousandths accuracy. Alright, so this is really cool, that we can utilize Excel. And we don't even really have to know anything about a derivative or how to solve a derivative or differential equation. All we have to do is just be able to program the algorithm. The hardest part is just programming the first iteration, and after that, just making sure you stay consistent with your cells each time. So hopefully this helps you to be able to show how to use Excel to program the improved Euler's method for solving for approximating the solution to a first order differential.